Welcome to GeoMethod channel. Here is the original problem. Three tangent circles sit inside a tall rectangle. The small radius is 1, the large radius is 2, the long side is 3 plus 2√6, and we want the middle radius R2. Pause here if you want to try the problem first. First, anchor the givens. The top small circle has radius 1, the bottom large circle has radius 2. These two numbers will be used again and again, so keep them visible. Now, name the unknown. The middle circle is the target circle, and its radius is R2. We will solve for this one, radius. Next, read the rectangle size carefully. In this tall picture, the long vertical side is the given length, 3 plus 2√6. Before we do algebra, name the contact points. A' is where circle 3 touches the left side, and D' is where circle 3 touches the right side. We will not assume anything about the line through them yet. Now use the tangent radius theorem. At a point of tangency, the radius to that point is perpendicular to the tangent side. So O₃A' is perpendicular to the left side, and O₃D' is perpendicular to the right side. Next, use a rectangle fact. The left and right sides of a rectangle are parallel, so the side through A' and the side through D' have the same direction. Here is the theorem tree step. If two lines are perpendicular to parallel lines, then those two perpendicular lines are parallel to each other. Therefore, O₃A' is parallel to O₃D'. Now use uniqueness. Through one point, there is only one line parallel to a given line. Since both lines pass through O3 and are parallel, they are actually the same line. So A', O3, and D' are collinear. With those points fixed, look at the auxiliary rectangle AD, D', A'. Its top side is AD and its bottom side is A', D'. Opposite sides of a rectangle are equal. Now use the collinearity. Since A', O3, and D' are on one line, the segment A', D' passes through the center of circle 3. So A', D' is a diameter equal to twice the radius. Since the large radius is 2, the diameter is 4. Therefore, segment AD, the short side of the rectangle, is 4. Now focus on the three centers. O1 is near the top, O2 is in the middle, and O3 is near the bottom. The whole solution will use distances between these centers. We draw the two useful center links, O1 to O2 and O2 to O3. These are useful because tangent circles give exact center distances. The target has not changed. We are still trying to find R2. The rest of the setup is only there to create equations for it. Keep both rectangle side lengths in mind. The tall side is 3 plus 2√6. The short side is 4. We will measure center positions from the rectangle sides. Because circle 1 touches the left side, its center O1 sits 1 radius to the right of that side. So its side distance is 1. Circle 1 also touches the top side. That means O1 is 1 radius below the top. This fixes the top offset. For circle 3, the radius is 2. Since it touches the left side, O3 is 2 units to the right of that side. Circle 3 also touches the bottom side, so O3 is 2 units above the bottom along the tall direction. For the target circle, the center O2 is R2 units away from the right side. Since the short side is 4, its distance from the left side is 4 minus R2. Now, connect the centers. These two orange links are not decoration. They are the hypotenuses of the two right triangles we are about to use. Circle 1 and circle 2 touch externally. For externally tangent circles, the distance between centers is the sum of the radii. So O1, O2 is R1 plus R2. The same tangent circle fact applies to circle 2 and circle 3. Their center distance is R2 plus R3. Now, name the vertical pieces. Let A be the upper center gap, and let B be the lower center gap. These are measured along the tall side. Both A and B are positive lengths. Visually, O₁ is above O₂, and O₂ is above O₃. So each gap has a real positive length. For the first triangle, compare the side distances of O₁ and O₂ from the left side. O₂ is 4 minus R2, while O₁ is 1. The across rectangle gap is 3 minus R2. For the second triangle, compare O₂ and O₃ from the left side. O₂ is 4 minus R2 and O₃ is 2, so that across rectangle gap is 2 minus R2. Now apply the Pythagorean theorem to the first right triangle. Its legs are A and 3 minus R2. Its hypotenuse is R2 plus 1. Apply the same theorem to the second right triangle. Its legs are B and 2 minus R2. Its hypotenuse is R2 plus 2. For the first equation, isolate A squared. Move the across rectangle square to the right side. For the second equation, do the same thing for B squared. We now have two difference of squares expressions. Here is the algebra pattern we will use. A square minus another square factors as difference times sum. Since A and B are lengths, we will take positive square roots later. We do not use negative roots for geometric lengths. Start simplifying the first difference of squares. The difference factor is R2 plus 1 minus 3 minus R2. Now, compute the matching sum factor. The sum is R2 plus 1 plus 3 minus R2. The R2 terms cancel, leaving 4. Multiply those two factors. This gives A squared equals 2R2 minus 2 times 4. Clean that product. The first triangle gives A squared equals 8 times R2 minus 1. Now take the positive square root. The length A is root of 8 times R2 minus 1. This also tells us the expression inside the root must be non-negative. So R2 is at least 1. Now simplify the second difference. The difference factor is R2 plus 2 minus 2 minus R2. The matching sum factor is R2 plus 2 minus R2. Again, the R2 terms cancel, leaving 4. Multiplying gives B squared equals 2R, 2 times 4. So the second triangle gives B squared equals 8R2. Taking the positive square root, B equals root of 8R2. The second root only requires R2 to be non-negative. The first condition, R2 at least 1, is stronger. Now, define the O₁ to O₃ vertical gap. The notation vertical bar O₁ O₃ vertical bar sub AB means the part of the O₁ to O₃ separation measured along the tall side AB. It equals the tall side minus the top radius and the bottom radius. Substitute the known values. The tall side is 3 plus 2 root 6, then subtract 1 and subtract 2. The ordinary numbers cancel cleanly. 3 minus 1 minus 2 is 0. So the O₁ to O₃ vertical gap is 2 root 6. That same O₁ to O₃ vertical gap is made from the two pieces A and B. Therefore, A plus B equals 2 root 6. Now, substitute our formulas for A and B. This creates one equation with only R2 left. Both roots contain a factor of 8. We separate root 8 from each term. Now factor out the common root 8. The remaining expression is root of R2 minus 1 plus root of R2. Simplify root 8. Since 8 is 4 times 2, root 8 is 2 root 2. Divide both sides by 2. This leaves root 2 times the parentheses on the left and root 6 on the right. Now divide by root 2. Root 6 over root 2 is root 3. So the equation becomes root of R2 minus 1 plus root R2 equals root 3. To make the last algebra cleaner, set u equal to root R2. Since R2 is a radius, u is positive. Then R2 becomes u squared. So root of R2 minus 1 becomes root of u squared minus 1. Move u to the right side, we get root of u squared minus 1 equals root 3 minus u. Before squaring, check the right side. It must be non-negative, so u is at most root 3. Now square both sides. This is the step where the radical disappears. Expand the square on the right carefully. Root 3 minus u squared gives 3 minus 2 root 3u plus u squared. Now, the u squared terms cancel on both sides. That leaves a simple linear equation. Move the constants to isolate the u term. We get 2 root 3 times u equals 4. Divide by 2 root 3. So u equals 2 over root 3. Finally, return to R2. Since u is root R2, R2 is u squared. Squaring 2 over root 3 gives 4/3. So the target radius is 4/3. Let us check the first gap. Substitute 4/3 into the formula for A, and it gives 2 root 6 over 3. Now check the second gap. Substitute 4/3 into the formula for B, and it gives 4 root 6 over 3. Add those two gap lengths. 2 root 6 over 3 plus 4 root 6 over 3 equals 2 root 6, exactly as required. Here is the idea in one pass. The rectangle gives the total O₁ to O₃ vertical gap. A plus B equals 2 root 6. The first right triangle gives A squared equals 8 times R2 minus 1. The second right triangle gives B squared equals 8R2. Substituting those two lengths into A plus B gives the single radical equation. A short substitution with u equal to root R2 solves the radical equation. Before we close, notice the style of the proof. Even the collinearity of A prime, O₃, and D prime was derived from smaller facts: tangent radius perpendicular, rectangle sides parallel, and uniqueness of a line through a point. That is the theorem tree. It is how geometry becomes a system, not just a picture. Therefore, the target circle radius is 4/3. That is the value of R2. So, the target radius is 4/3. The important lesson is not only the answer, but the theorem tree behind it. We used tangency, parallel sides, right triangles, and then a radical equation. If you enjoyed this GeoMethod walkthrough, please subscribe, click like, and leave a comment with a problem or an alternative solution you would like me to discuss.